Deep within the constellation Sagittarius, lurking at the gravitational heart of our Milky Way galaxy, there exists something truly extraordinary. It is called Sagittarius A star, and it represents one of the most extreme objects that nature has ever created. This is not a star in any conventional sense, but rather a supermassive black hole with a mass equivalent to roughly 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury. The sheer density of this object defies easy comprehension, yet in recent years, we have managed to capture its portrait and unlock many of its deepest secrets. On May 12, 2022, astronomers revealed the first direct image of Sagittarius A star, marking only the second time humanity had successfully photographed the shadow of a black hole. This achievement required the coordination of 8 radio telescopes scattered across the planet, from Hawaii to Antarctica, working in perfect synchronization to create what is essentially an Earth-sized telescope. The image shows a glowing ring of superheated gas and dust, twisted and distorted by the immense gravity, with a dark central region representing the event horizon itself. What makes this image particularly remarkable is the challenge involved in capturing it. Unlike its larger cousin in the galaxy, Messier 87, which remains relatively stable over hours or days, Sagittarius A star changes its appearance in mere minutes, requiring scientists to sort through petabytes of data to find patterns in the chaos. The black hole sits approximately 26,000 light-years away from Earth, positioned in the direction of the constellation Sagittarius as seen from our vantage point. To put this distance in perspective, if you could travel at the speed of light, it would take you 26,000 years to reach this cosmic monster. Yet despite this enormous distance, the gravitational influence of Sagittarius A star extends throughout our entire galaxy, serving as the anchor point around which hundreds of billions of stars, including our own Sun, slowly orbit. One of the most compelling pieces of evidence for the existence of this supermassive black hole comes from decades of careful observation of stars in its immediate vicinity. Astronomers have tracked individual stars, given designations like S2, S4, and S62, as they whip around the invisible mass at breathtaking speeds. The star S2, one of the brightest and most extensively studied, completes an entire orbit around Sagittarius A star in just 16 years. At its closest approach, this star reaches speeds of nearly 5,000 kilometers per second, or about 1.7% the speed of light. That is roughly 15 million kilometers per hour, fast enough to circle the Earth's equator in less than 3 seconds. These orbital velocities provide astronomers with precise measurements of the mass concentrated at the galactic center, confirming that nothing but a supermassive black hole could create such extreme gravitational effects in such a compact region. The star S62 holds an even more extreme record. In 2020, researchers confirmed that this star had achieved the closest known approach to Sagittarius A star, coming within just 16 light-hours of the event horizon. For context, 16 light-hours is roughly the distance from the Sun to Uranus. At this proximity, S62 experienced time dilation, effects predicted by Einstein's theory of general relativity, with time passing measurably slower for the star than for distant observers. The star's velocity at closest approach exceeded 8% of the speed of light, making it one of the fastest moving stars ever detected in our galaxy. The discovery of Sagittarius A star as a supermassive black hole was not a sudden revelation, but rather the culmination of decades of painstaking research. In the early 1970s, astronomers detected a mysterious radio source at the galactic center, which they named Sagittarius A. This radio emission comes from the region immediately surrounding the black hole, where magnetic fields accelerate charged particles to tremendous energies. The brightest point within this radio source became known as Sagittarius A star, and it remained an enigma for many years. Was it a dense cluster of stars, a massive neutron star, or something else entirely? The breakthrough came in the 1990s when astronomers Reinhard Genzel and Andrea Ghez began independently tracking the motions of stars near the galactic center using advanced infrared telescopes. Infrared light can penetrate the thick clouds of dust that obscure our view of the galactic center in visible light, allowing these researchers to map stellar orbits with unprecedented precision. Year after year, they watched stars accelerate and decelerate, tracing elliptical paths around an invisible point. The only explanation consistent with these observations was the presence of a supermassive black hole. For this groundbreaking work, Genzel and Ghez were awarded the Nobel Prize in Physics in 2020, sharing the honor with Roger Penrose for his theoretical contributions to black hole physics. What makes Sagittarius A star particularly fascinating is its relative quietness compared to other supermassive black holes. Many galaxies harbor actively feeding black holes at their centers, known as active galactic nuclei, which blaze with the light of 1 trillion suns as they devour surrounding matter. These quasars can outshine their entire host galaxies and be detected from across the observable universe. Sagittarius A star, by contrast, is remarkably dormant. It consumes only a tiny fraction of the available material in its vicinity, producing relatively feeble radiation compared to its mass. If Sagittarius A star were as active as some quasars, the night sky would be dramatically different, with the galactic center shining brighter than the full moon and bathing Earth in high-energy radiation. However, this does not mean that Sagittarius A star is completely inactive. The black hole does experience occasional flares, sudden brightenings that can increase its luminosity by factors of 10 to 100 in the span of an hour or less. These flares occur in multiple wavelengths, from radio waves to X-rays, and are thought to result from magnetic reconnection events in the hot plasma swirling just outside the event horizon. Astronomers have observed that these flares happen several times per day, though their exact trigger mechanism remains a subject of active research. Some theories suggest that the flares occur when small clumps of material plunge into the black hole, temporarily brightening the accretion flow. The environment immediately surrounding Sagittarius A star is one of the most extreme in the galaxy. Within a few light years of the black hole, stars are packed far more densely than in our solar neighborhood. In the region known as the central parsec, stellar densities can reach millions of stars per cubic light year, compared to just a handful in the sun's vicinity. This crowded environment leads to frequent stellar interactions, with stars occasionally colliding or passing close enough to gravitationally perturb each other's orbits. Some stars in this region have been ejected entirely from the galactic center, flung outward at speeds exceeding 1,000 kilometers per second, destined to wander through interstellar space for billions of years. Remarkably, despite the hostile conditions, new stars continue to form near Sagittarius A star. Astronomers have discovered massive young stars, only a few million years old, orbiting within a fraction of a light year from the black hole. This was initially puzzling, because the strong tidal forces near such a massive object should disrupt the gas clouds needed for star formation. The current hypothesis is that these stars formed farther out and later migrated inward, or that they formed in massive gas disks that were dense enough to resist tidal disruption. These young stars are extremely luminous and short-lived, and they will eventually exhaust their nuclear fuel and explode as supernovae, adding to the already chaotic environment of the galactic center. The event horizon of Sagittarius A star the boundary beyond which nothing can escape, has a diameter of approximately 44 million kilometers, or about 60 million times the diameter of a typical star like our Sun. This might sound enormous, but it is actually relatively small for a supermassive black hole of this mass. If you could somehow observe Sagittarius A star from a distance of 1 astronomical unit, the average Earth-Sun distance, it would appear as a dark circle subtending about 3 degrees on the sky, roughly 6 times the angular diameter of the full moon. Of course, you would never survive such proximity, as the tidal forces would tear apart any object long before it reached the event horizon. The rotation of Sagittarius A star adds another layer of complexity to its structure. Like most black holes, Sagittarius A star is believed to rotate rapidly, dragging space-time itself into a swirling motion around it. This effect, known as frame dragging, means that anything orbiting close to the black hole is forced to rotate in the same direction as the black hole itself, regardless of its initial trajectory. The rotation also influences the shape of the event horizon, causing it to bulge slightly at the equator. Recent observations suggest that Sagittarius A star may be rotating at close to its maximum possible rate, with the equator of the event horizon moving at nearly the speed of light. Understanding the properties of Sagittarius. A star has profound implications for our understanding of galaxy formation and evolution. Nearly every large galaxy observed in the universe appears to harbor a supermassive black hole at its center, with masses ranging from millions to billions of solar masses. There exists a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its central bulge and the velocities of stars within it. This suggests that black holes and galaxies grow together through some linked process, though the exact mechanisms remain unclear. Did the black holes form first, providing gravitational seeds around which galaxies assembled? Or did galaxies form first, funneling gas into their centers to create the black holes? Current evidence suggests a complex interplay between both processes, with black holes and galaxies influencing each other's growth throughout cosmic history. The journey of light from the vicinity of Sagittarius A star to Earth is itself an epic adventure. The photons we detect from the glowing material around the black hole must traverse 26,000 light-years of interstellar space, passing through vast clouds of gas and dust that absorb and scatter much of the light. This is why infrared and radio observations are so crucial for studying the galactic center. These longer wavelengths can penetrate the obscuring material that blocks visible light, allowing astronomers to peer into the heart of our galaxy. Along the way, the light also experiences gravitational lensing, being bent and distorted by the gravity of intervening stars and dark matter, though these effects are generally too subtle to measure directly. One of the strangest predictions of general relativity, confirmed by observations of matter near Sagittarius A star, is the phenomenon of gravitational redshift. As light climbs out of the deep gravitational well surrounding the black hole, it loses energy, causing its wavelength to stretch and its frequency to decrease. This means that light emitted in the visible part of the spectrum near the event horizon might arrive at Earth as infrared radiation, having been shifted to longer wavelengths by the extreme gravity. For the innermost stable circular orbit around Sagittarius A star, the gravitational redshift factor is substantial, with photons losing a significant fraction of their energy in the journey outward. The temperature of the material surrounding Sagittarius A star varies dramatically depending on distance from the event horizon. The accretion flow, the slowly spiraling stream of gas and dust falling toward the black hole, can reach temperatures of billions of degrees in its innermost regions. At these temperatures, matter exists in a plasma state, with electrons stripped from atomic nuclei, and emits primarily X-rays and gamma rays. Farther out, in the region imaged by the Event Horizon Telescope, temperatures are lower, but still extreme by everyday standards, hovering around 10 billion degrees Kelvin. This superheated plasma glows brightly in radio waves, creating the luminous ring visible in the famous image. The magnetic fields threading through the accretion flow around Sagittarius A play a crucial role in determining how matter behaves as it spirals inward. These fields, generated by the motion of charged particles in the plasma, can become twisted and amplified as they are dragged along with the infalling material. In some cases, the magnetic field lines can become so tangled that they snap and reconnect, releasing vast amounts of energy in the process. This magnetic reconnection is thought to power the flares observed from Sagittarius A star, and may also launch powerful jets of material along the black hole's rotation axis, though such jets have not been definitively detected from our galactic center. Throughout human history, the center of our galaxy has been invisible to the naked eye, hidden behind the thick veil of dust that pervades the galactic plane. Ancient astronomers gazed at the band of the Milky Way stretching across the night sky, not knowing that they were looking at the collective light of billions of stars in our galaxy's disk, nor that somewhere in the direction of Sagittarius lay a gravitational monster beyond their wildest imaginings. It was not until the 20th century, with the development of radio astronomy and infrared detectors, that we could begin to pierce this veil and study the galactic center in detail. The broader question of how supermassive black holes form remains one of the great unsolved mysteries in astrophysics. For a black hole to reach millions or billions of solar masses, it must either form from an extremely massive seed or grow rapidly through continuous feeding and mergers with other black holes. The seeds of supermassive black holes might have been massive stars that formed in the early universe, collapsing directly into black holes with masses of hundreds or thousands of suns. Alternatively, dense star clusters in the centers of young galaxies might have merged into massive black holes through a runaway process. Once formed, these seed black holes would grow by accreting gas from their surroundings and by merging with other black holes during galactic collisions. Black holes fundamentally challenge our intuitions about the nature of reality. They represent regions where gravity becomes so strong that the usual rules of physics break down. At the event horizon, the escape velocity equals the speed of light, making it impossible for anything, including light itself, to escape once it crosses this boundary. Inside the event horizon lies the singularity, a point where matter is crushed to infinite density, and the curvature of spacetime becomes infinite. At least, this is what Einstein's equations predict. But most physicists believe that quantum effects, not yet understood, must prevent the formation of true singularities. Developing a theory that successfully merges quantum mechanics with general relativity remains one of the greatest challenges in theoretical physics. Time itself behaves strangely near a black hole. As you approach the event horizon, time slows down relative to a distant observer. An astronaut falling toward Sagittarius. A star would experience time normally from their own perspective, but to someone watching from far away, they would appear to slow down, becoming frozen at the event horizon, their image growing dimmer and redder as they asymptotically approach the point of no return. This time, dilation effect is not just a theoretical curiosity, but has been measured directly in the orbits of stars around Sagittarius A star, where the predictions of general relativity have been confirmed to exquisite precision. The story of Sagittarius A is ultimately a story about the power of human curiosity and ingenuity. From our small planet orbiting an unremarkable star in the outer reaches of the galaxy, we have managed to detect, measure, and even photograph an object 26,000 light-years away that emits no light of its own and exists in one of the most extreme environments imaginable. We have done this through centuries of accumulated knowledge, from the ancient astronomers who first mapped the stars, to Einstein who reimagined the nature of gravity, to the modern scientists who built the incredible instruments that make such observations possible. Looking ahead, our understanding of Sagittarius A star will continue to deepen. Future observations with even more sensitive instruments will reveal new details about the accretion flow and the environment near the event horizon. Projects like the Event Horizon Telescope continue to improve, with plans to add more telescopes to the global array and observe at shorter wavelengths, which will produce sharper images with finer details. Space-based observatories will study the galactic center across the entire electromagnetic spectrum, from radio waves to gamma rays, building a comprehensive picture of the physics at play in this extreme environment. Scientists are also developing new techniques to probe even deeper into the mysteries of Sagittarius A star. Gravitational wave observatories like LIGO and the future space-based LISA mission may eventually detect waves generated by small objects spiraling into the black hole or by the black hole's interaction with its environment. These gravitational waves would carry information about the space-time structure near the event horizon, providing tests of general relativity in the strongest gravity regime accessible to observation. The existence of Sagittarius A star also raises profound questions about the fate of matter that falls into black holes. According to classical general relativity, information about anything that crosses the event horizon is lost forever, erased from the universe. However, this appears to conflict with the principles of quantum mechanics, which hold that information cannot be destroyed. This paradox, known as the black hole information problem, has sparked decades of debate among physicists and has led to new insights about the nature of spacetime, quantum entanglement, and the relationship between gravity and quantum theory. In the grander scheme of cosmic evolution, Sagittarius A star represents a common feature of the universe. Supermassive black holes are found at the centers of most large galaxies, suggesting that they play a fundamental role in how galaxies form and evolve. The energy released by matter falling into these black holes can regulate star formation in their host galaxies, heating surrounding gas and preventing it from cooling and collapsing to form new stars. This feedback process helps explain why galaxies do not convert all their gas into stars, and why the universe contains a mix of small and large galaxies with diverse properties. As we contemplate the vast scales of space and time involved in the story of Sagittarius A star, it is worth reflecting on our own place in the cosmos. We live in a galaxy dominated by a supermassive black hole, orbiting it at a stately pace that will take hundreds of millions of years to complete. The Sun has likely completed about 20 such orbits since it formed 4.5 billion years ago, and will complete perhaps another 20 before it exhausts its nuclear fuel and ends its life as a white dwarf. Throughout all of this, Sagittarius A star will endure, outlasting stars, planets, and perhaps even galaxies themselves, a monument to the strange and wonderful laws of physics that govern our universe. The black hole will continue to grow, albeit slowly, as it accretes material and merges with other black holes during future galactic collisions. In roughly 4 billion years, our Milky Way galaxy is predicted to collide with the Andromeda galaxy, our nearest large galactic neighbor. When this happens, the supermassive black holes at the centers of both galaxies will eventually spiral together and merge, creating an even more massive black hole, and releasing tremendous amounts of energy in the form of gravitational waves. This merger will fundamentally reshape the structure of the resulting galaxy, potentially triggering bursts of star formation and redistributing stars and gas on galactic scales. Even farther into the future, on timescales of trillions of years, the universe will continue to expand, and galaxies will drift apart as space itself stretches. Eventually, most galaxies will become isolated, unable to interact with their neighbors. Stars will continue to form, live, and die, but the raw materials for new stars will slowly be depleted. In this far future, supermassive black holes like Sagittarius A star will be among the last remaining active objects, slowly growing as they consume the occasional wayward star or gas cloud. Even black holes, however, are not eternal. Through a quantum mechanical process called Hawking radiation, black holes slowly evaporate, emitting particles and losing mass over extraordinarily long timescales. For a black hole, the mass of Sagittarius A star, complete evaporation would take approximately 10 to the power of 100 years, a time so long that it defies meaningful comprehension. The study of black holes has revealed that the universe is far stranger and more wonderful than our ancestors could have imagined. These objects challenge our understanding of space, time, matter, and energy, pushing the boundaries of physics to their limits. They serve as natural laboratories for testing our most fundamental theories, under conditions that can never be reproduced on Earth. Every observation of Sagittarius A star teaches us something new about how the universe works, from the behavior of matter in extreme gravity to the large-scale structure of galaxies and the evolution of the cosmos itself. In the end, the ferocious beast at the center of our galaxy is not something to fear, but something to marvel at. Sagittarius. A star represents the culmination of physical processes that have been unfolding for billions of years, a testament to the creative power of gravity and the complex dance of matter and energy that fills the cosmos. It reminds us that we are part of something much larger than ourselves, participants in a grand cosmic story that began with the Big Bang and will continue for eons to come. As we gaze toward the heart of our galaxy, we are not just looking at a black hole, but at a gateway to deeper understanding, a mystery that continues to inspire wonder and drive us to explore the unknown.